Alright, we're going to consider acceleration in this video. And the first thing I want you to do is consider the following scenarios. Imagine that you roll a golf ball across a table, and while you're rolling you do the following three things. The first time you roll it, while it's rolling, you change its speed but not its direction. So you might blow on the back of the ball while it's moving to speed it up as long as it doesn't change direction, or you might tap the top just a little bit so that it slows down, not changing its direction. Number two, you might change its direction but not its speed. So you might put your hand in front of it to turn it a little bit, but maybe give it a slight push to keep it moving at the same speed, because you might notice that if you try to turn the ball, it will slow down, and we don't want to change the speed. Or you might pass it back and forth between a buddy and yourself, again changing directions going forward and then backward, but you're not changing the speed. Thirdly, you might change the speed and the direction. Okay, you could change the direction and allow the ball to slow down. You might blow on the back of the ball and speed it up, and maybe perhaps change direction at the same time. Perhaps you would blow on the ball from an angle, something like that. But my question is, as you consider these things, think about for a minute, which of these three, if any of them, constitute acceleration? In which instance were you accelerating the ball? Think about that for a second. Alright, to start to answer that question, I want to show you what acceleration actually is. Acceleration is change in velocity divided by the time needed to make that change. And if we remember what change in velocity means, I might go back to this slide and see if you might want to change your answer. My guess is that most of you said that 1 is acceleration and 3 is acceleration because we could change the speed. In other words, we could speed the ball up. And that shows me one thing, is that most students, when they come into physics, they enter with the concept of acceleration, which is that acceleration is speeding up. And we use that commonly in real life. If we're accelerating in our cars, that means we're speeding up. But in physics, acceleration is simply a change in velocity. And if you remember, velocity is speed and direction. It's a vector quantity. It incorporates both speed and direction. So if we look at all of these, all three of these instances are changing the velocity of the ball. This one is changing speed but not the direction. This one is changing direction but not the speed. Even though the speed isn't changing, the direction is, therefore the velocity is changing. Or we're changing speed and direction. That's both. That's for sure changing the velocity. But you might not realize, for instance, number two, if you're in your car and you're going around a curve but you're not losing speed, you're keeping your speed, that is acceleration. You are accelerating even though you're not changing speed, because the definition of acceleration in physics is a change in velocity, which could also include a change in direction. That formula for acceleration is this, and it is in your equation chart. I think it's number 3 in your equation chart. A is delta V over delta T. Delta is the symbol we use for change. So this is change in velocity divided by the change in the time it needs to make that change. So this is how much you sped up or slowed down, and then divided by how long it took you to do that, to make that change. This formula, delta V over delta T, in order to calculate delta V over delta T, in your notes I want you to write this, that VF minus VI is what delta V means. In other words, to calculate the change in velocity, we must have the final velocity and the initial velocity. And it's very important that we do it in this order, that we do final velocity minus initial velocity and not the other way around. It's extremely important that we do that, because it'll change the direction of the velocity if we don't. VF, notice, is final velocity, VI is initial velocity. So if we rearrange this, I don't like fractions, I want to get T out of the numerator. I can multiply both sides by T and then solve the resulting equation for VF. What I get is an equation that looks like this. VF equals VI plus AT. Again, VF and VI still are final velocity and initial velocity. But this is now our first kinematic equation. It's equation number 4 in your equation chart. It's the exact same equation as this one. They're just rearrangements of each other. But this one is important because it's the first kinematic equation that we're going to be working with. This one does not include distance in it, but we can do a lot with this. Again, these are the same formulas. The units for acceleration are very important to know. It's extremely important that you know that the units for acceleration in physics are always going to be meters per second squared. And in this class, you will never have to do a conversion with acceleration. You will always be given acceleration in meters per second squared. And when you calculate it, it should be calculated in meters per second squared. Now, that's not to say that the velocities you use to calculate acceleration won't require conversion, because sometimes those will. Uniform acceleration is a really interesting concept. That just means constant, unchanging acceleration. In other words, you're gaining the same amount of velocity every second. And in order to do that, to show you that, I first need to prove this meters per second squared to you. All right, I want to prove to you that the units for acceleration are meters per second squared. We measure speed in physics in meters per second, or velocity, and if acceleration is a measure of how quickly velocity changes, then I want to know how many meters per second I gain or lose every second. So that's why the units for acceleration are meters per second, which this is the same thing as meters per second times 1/seconds. Multiply straight across on those, and that gives you meters per second squared. So what that means is, for instance, if my acceleration equals 1 meter per second squared, that means that every second I'm gaining 1 meter per second in speed. So at the end of 1 second, my speed is 1 meter per second if I start at 0. At the end of 2 seconds, my speed is 2. At the end of 3 seconds, it's 3, etc., etc.